Alright, hi everyone. So, I was gonna go to sleep. I was quite tired, and it's already 10 p.m. But I got this jolt of energy, and I thought, hey, let's do this. Let's do something here. So, last thing we did is we have a window, right? We created the window, and it works, and that's all great and stuff. The next step would be to connect Vulkan with the operating system or the windowing system in Windows. And usually the way you do that is you create a context and a swap chain, right? As far as I know, that's how you do it in OpenGL. You have a context that you create. Actually, in OpenGL, you create a legacy context and then you create a new context on top of the legacy context. Then you delete the legacy context. It's a whole mess, fucking disaster. Um, so Yeah, I don't know how it's done exactly with Vulkan. I guess we'll figure it out. Um, so I've had very extremely little experience with Vulkan. Um, I've tried doing this a few years ago, and I kind of got bored, or I got busy. I don't know what the hell happened, but I kind of gave up. And so this time, hopefully, I won't. I won't give up. So let's see. All right, so let's start reading and figure out what's going on. So okay. All right. So OpenGL is a really old API, right? It was made in the freaking 1993, 1994, around that. When is open now? When did OpenGL came out? Yeah, 1992. Um, it's been updated obviously, but it's kind of structured and designed on the architecture of old graphics cards, um, which is very old. So Vulkan just came in and kind of was replacing that whole thing. Um, all right, there's a lot of setup before you get started with your first triangle. Like there's so much goddamn thing. There's so much that you have to do before drawing that first triangle. The driver doesn't hold your hands. The graphics drivers doesn't hold your hand. You have to tell it exactly what you want, and you have to set up everything, which is kind of cumbersome. But the first time you do it is, you only have to do it once, basically. So these guys are gonna use GLFW for the Windows creation. We're not using GLFW. GLFW is awesome, by the way. If you want to use it, go ahead. It just abstracts everything for you. It supports multi-monitor, high DPI. It does Vulkan OpenGL stuff. Like allows you to. It's a basically windowing system, right? You don't have to create a window for you, or you don't have to deal with mouse and keyboard support. That's all done within the library, which is awesome, right? But I don't wanna. I wanna do everything from scratch. So we're not using GLFW, but they are using GLFW. So I think I need a different tutorial to show me how to set up Vulkan, or maybe they have a section that tells me how to do that without GLFW. I have no idea. We'll see. We'll figure that out at some point. But that's unfortunate. Unfortunate that you're using GLFW and not like Windows from scratch. So we'll see how I have to deal with that. All right, cool. So that was kind of the introduction, which is cool. Let's go to the overview. Oh Lord, overview. All right, let's get reading. It's gonna be a few days before, not days, maybe probably a week or more before we get that first triangle on the screen. Let's see. Alright, just like the previous graphics APIs, Vulkan is designed as a cross-platform abstraction over the GPU. The problem with most of these APIs is that the era in which they were designed featured graphic hardware that was mostly limited to configurable fixed functionality. Now, yeah, that's true, right? So OpenGL and DirectX 9, 10, and 11, those were all designed around the idea of fixed function pipeline. Well, not so much 11 and 10, but certainly 8, 9, 6, 5, those DirectX versions. And so they're quite old, and we kind of carry a lot of those design choices that were made in 2001, 1990s, 2005, around that time into the modern era, which is very, very bad because graphics cards have changed tremendously since 2000, even 8, 10. Like 2010 is 10 years ago. That's insane to think about it, right? And Vulkan came out in 2016, around that time. So yeah, programmers had to provide the vertex data in a standard format, and were at the mercy of the GPU manufacturer with regards to lighting and shading and options. Right. So fixed pipeline basically was, every game kind of looked the same, right? There was no special effects. Well, it was very hard to do if you were able to do it. The lighting was very, very similar for all games. Basically, if you wanted lighting, you just tell the API, graphics API, hey, turn on lighting, and that's it, really. But later on, they introduced shaders, and with shaders, you were able to do custom lighting and custom vertex stuff, which is the new thing with DirectX 9, DirectX 10, OpenGL 3.2, around that. As graphics card architectures matured, they started offering more and more programmable functionality. All this new functionality had to be integrated with the existing API somehow. This resulted in a less than ideal abstraction and a lot of guesswork on the graphics driver side to map the programmer's intent to modern graphics architecture. That's why there are so many driver updates improving performance in games, sometimes by significant margin. Because of the complexity of these drivers, application developers also needed to deal with the inconsistencies between vendors, like the syntax that's accepted by shaders, right? So this is why there are a lot of graphic driver updates, and every new release of a new game, you get a driver update. So if I go to the AMD website right now, if I just type AMD, right? If I check out the latest driver 9.1, you go to release date, you can see that it added support for Deathloop, Call of Duty, AMD Smart Access Memory for Radeon RX 5000. Oh, that's cool. And Windows 11 support, right? But the first two is games. They added support for those games. And so the driver manufacturer, like AMD and NVIDIA, they work with the developers to kind of get their games supported or optimize their games more on those graphics cards, right? And that's really cumbersome and kind of annoying, right? So ideally with Vulkan, you want to do that less and less, which would be nice. Aside from the new features, the past decades also So a new influx of mobile drivers with powerful graphics hardware. These mobile GPUs have different architecture based on their energy and spec requirement. One such example is tiled rendering, which would be benefit from improved performance by offering the programmer more control over this functionality. Another limitation, orienting from the age of these APIs is limiting multi-threading support, which can result in bottleneck on the CPU, right? Okay, so back then you had one CPU core or two CPU core at max, right? So you had your CPU with the Pentium 4, you just had a single core. With the Pentium 3, you had a single core, right? And then AMD came out, AMD Athlon, which came out with 2 cores, and then was the Athlon X2. And Pentium 4 came out with 2 cores, and then it came out the Core 2 Duo and Core 2 Quad, and then i3, i7, and so on and so forth, right? And so until DirectX, to this day, if you're using DirectX and OpenGL 4.5 or whatever, multi-threading support is very limited. Yes, there is multi-threaded support. It's just that it is extremely hard to do, as far as I'm aware. And it's not great. It's not the greatest way of doing it. And so historically, the graphics render only ran on a single core. So you had all this power. You had 4 cores that just sat there and did absolutely nothing. And the graphic render only worked on a single core, right? Which wasn't great. So these guys were just sitting here and doing absolutely nothing. And then developers were like, okay, well, the graphics can run on this core, networking can run on this core, audio can run on this core, and then, I don't know, just have physics run on the 4th core, right? And that's how they split it, which is not super great because rendering is one of the most important things, and it's still sitting on a single core. Not great at all. And so with Vulkan, the way it's architectured, it has a job system kind of sort of thing. You have a frame buffer, as far as I remember. You have multiple buffers, buffer queue, command buffers, something like that, and you just tell them, hey, I want to render a tree. So this guy renders trees. This guy render, I don't know, grass. This guy render cars in the game, and so all of these just work on multiple cores, which is kind of cool. Something along these lines. We'll read about it in a bit more later on. But so the big downsides of OpenGL and kind of OpenGL and DirectX 11 and under is that the multi-threaded functionality was kind of shitty, like really shitty. And so Vulkan and DirectX 12 and Metal, the Metal API for with Apple, is trying to solve that problem, right? Vulkan solved these problems by being designed from scratch for modern graphics architecture. It reduces driver overhead by allowing programmers to clearly specify their intent using more verbose API and allow multiple threads to create and submit commands in parallel. It reduces inconsistencies in the shader and compilation by switching to standardized bytecode format with a single compiler. Lastly, it acknowledges the general purpose processing capabilities for modern graphics cards by unifying by unifying the graphics and compute functionality into a single API. It's kind of cool. So yeah, Vulkan solving problems. Where does it take to drag a triangle? Oh Jesus fuck. We'll now look at an overview of all the steps it takes to render a single triangle in a well-behaved Vulkan application program. All of the concepts introduced here will be elaborated on in the next chapter. This will give you a big picture of, okay, cool. So instance and physical device selection. A Vulkan application starts by setting up the Vulkan API through VK instance. Okay, so we need an instance of Vulkan. An instance is created by describing your application and API extensions you will be using. After creating the instance, you can query for Vulkan supported hardware and select one or more VK physical device to use the operation. You can query for properties like VRAM size and device capability to select desired device. For example, to prefer using dedicated graphics cards. Oh, Jesus Christ. Okay, so Vulkan can work on multiple hardware at the same time, right? And this is why kind of SLI and Crossfire is dead or dying, or they died basically. Vulkan can just issue commands on multiple graphics or multiple physical devices at the same time, which is kind of great. Oh, what? Oh, whoops! No, don't go there. I wanted to check something. Hey, your tile rendering. What? Tile rendering. Tile rendering is the process of subdividing computer graphics images by regular triangle. Optical. Is there any is okay? I've heard about tile rendering, something with how NVIDIA they use the thingy. So NVIDIA they do that kind of thing. So they split everything into tiles. It's kind of interesting. I'll look into this a bit more. I've heard it in one of the talks, NVIDIA talks. So we'll see. We'll go that. Okay. So yeah. So we need a VK instance, simple enough. And we need a physical device. All right. Logical device and Q families. After selecting the right hardware device to use, you need to create a VK device. Logical device. Okay, so after we select the physical device, we need to create a virtual or logical device where you describe more specifically which VK physical device feature you'll be using, like multi viewport rendering and 64-bit floats. You also need to specify which Q family you would like to use. Most operations performed Vulkan, like draw commands and memory operations, are synchronized asynchronously executed by submitting them to VKQ. The queues are allocated from queue families, where each queue family supports a specific set of operations in its queue. For example, there could be separate queue families for graphics, compute, and memory transfer operations. The availability of queue families could be used as distinguishing factor in physical device selection. It is possible for a device with Vulkan support to not offer any graphics functionality. However, all the graphics card with Vulkan support today will generally support all queues operation that you're interested in. Alright, that's cool. So you can have a Vulkan, you can have a Vulkan supported device that offers only compute, right? Or only graphics, or only, I don't know what are other queues there are. There's graphics, compute, or memory transfer. Sure, why not, right? So when you want a queue for support, I kind of see, does this device that you selected, does it support any graphics? And that's kind of what we want to do, right? We want graphics queues. We don't care much about compute or memory transfer. We'll see about memory transfer. Sorry. Oh Jesus. Okay, so we need to create a VK instance. Select a physical device. From the physical device, select a logical device. From the logical device, queue for all supported families and see whether we have a graphic queue that we want to select. We're going to select the correct graphic queue that we want with a specific, I don't know, the VRAM and shit. And then once we do that, we've selected our device. That's just the start. Okay, cool. Windows Surface and swap chain. Unless you're only interested in off-screen rendering, you will need to create a window to present rendering images to. Windows can be created with the native platform API library like GLFW. You'll be using Gelato Installer, but more about that in the next. Okay, cool. We'll need 2 or more components to actually render to a window. A window surface and a swap chain. Alright, so we need the window surface and the swap chain. Note that KHR postfix, which means that these objects are part of the Vulkan extension, HKR. The Vulkan API itself is completely platform agnostic, which is why we need to use standardized WSI Windows System Interface extension to interact with the Windows Manager. The Surface is cross-platform abstraction over Windows to render and generally instantiated by providing reference native window handler. Okay, HWND, that's the window, the handle. Okay, luckily you'll fill okay, cool. So you can, by the way, this is cool, right? You can have so OpenGL, you render on off-screen rendering, so you don't need a physical screen to render on. You can render on, I believe, textures and images, and kind of save them on the drive, which is kind of cool. But we're interested in rendering things on the screen, so we need to queue for, or we want to connect to the operating system, window management system. Now, Vulkan itself doesn't care about a window thing, right? That's not handled by Vulkan itself. It doesn't, like, Vulkan doesn't connect to a windowing system, right? Vulkan is more of multi-platform. It doesn't care what platform you're running on. So you can think of it this way. You can think of it as there's this thing called the Vulkan extension, KHR. Okay, this is communicating with the operating system. So this is the OS. Whatever OS you're running on, whether it's Windows, Mac, Linux, Android, whatever the hell, right? And you have Vulkan sitting over here, right? And Vulkan, so these guys are communicating with each other. There's a window over here, right? And so now, in order for Vulkan to render things, it kind of connects to HKR, right? And HKR, it's just the bunch of systems that they need to talk with the operating system. So Vulkan really doesn't care whether you're running on Windows, Mac, Linux, right? It just communicates with this layer, abstraction layer. And this abstraction layer connects with the operating system itself. Right, so this could be OS X, this could be iOS, this could be Android, this could be Linux, could be anything you want, right? So that's operating system communicating with this guy is communicating with Vulkan, and so Vulkan doesn't have to deal with the messiness of connecting to an operating system. All that is offloaded to like a different separate thing. Cool. So we need to get a Windows surface, VK surface, HKR, it's the extension. And we need to get the swap chain. Okay, the swap chain is a collection of render targets. Its basic purpose is to ensure that the images that we're currently rendering is different from the one that. Okay, oh Jesus, that was horrible reading. Let me try this again. Its basic purpose is to ensure that the image that we're currently rendering to is different from the one that is currently on the screen, right? Okay, so in a graphics API, you have basically usually two buffers. The back buffer, why is that a triangle? This is your back buffer, and this is your front buffer, right? This is your screen. This is what you see as the user, and rendering happens on the back buffer. So we render a triangle, we render a tree, we render a human, right? Whatever, and then we swap those buffers together. So this goes. The front buffer goes on the back, and the back buffer goes to the front. So now the player is seeing the back buffer, and the front buffer is going on the back, right? So now this is the front buffer. So these guys swap around, and then we write on this, and then they swap again, and then we write on this. So Vulkan is always writing to the back buffer, and the player is always seeing the front buffer. Now the reason this happens is to reduce tearing, to reduce artifacts, and to reduce just bullshit that you don't. It makes the image a little bit smoother, a little bit nicer, no artifacting, no tearing, and so on and so forth, right? So that's the job of the swap chain. The swap chain allows you to switch between those two targets. This is important to make sure that only complete images are drawn, right? We don't want to see half images. Every time we want to draw a frame, we have to ask the swap chain to provide us with an image to render to. When we finish drawing a frame, the image is returned to the swap chain for it to be presented on the screen at some point. The number of render targets, conditions for presenting finished images to the screen depend on the mode. Common present mode use double buffering or triple buffering. We'll look at these swap and swap chain. Okay. Some platforms allow you to render directly to the display without interacting with any window manager through VK HR display and VK swap chain extensions. These allow you to create surfaces that represent the entire screen and could be used to implement your own window manager, for example. Okay, cool. So we need the surface, and then we need the swap chain. All right, cool. Oh, Jesus fuck. Okay. Image, views, and frame buffers. To draw to an image acquired from the swap chain, we have to wrap it into a VK image view and a VK frame buffer. An image view reference a specific part of an image to be used. An image view reference a specific part of the image to be used, and the frame buffer reference image views that are to be used for colors, depth, stencil targets. Because there could be many different images in the swap chain, we'll primitively create an image view and a frame buffer for each of them. So like, alright, okay. I don't understand that. Hold on, I need to read this again. Okay, so you have a frame buffer, which is kind of the entire image, and an image view, which is part of the image. Sure, I suppose. Okay. Why? I don't know. Render passes. Render passes in Vulkan describe the type of images that that are used during rendering operations, how they will be used, and how their contents should be treated. In our initial triangle rendering application, we'll tell Vulkan that we will use a single image as color target, as we want to clear the solid color during operations. Render passes only describe the type of images we are actually blended. Okay, so we can have multiple render passes and we can have multiple frame buffers. One frame, I believe that's correct. One frame buffer could be for color, another frame buffer for depth information, another frame buffer for stencil information. Especially if you're doing something like deferred rendering, you'd need multiple frame buffers. Each frame buffer contain information about the scene differently, and so yeah, a color buffer is enough at the very beginning. Okay, the graphics pipeline. Oh shit, here's the hard stuff. Alright, I mean, that wasn't all hard. I don't know. This is what this is. Okay, cool. The graphic pipeline in Vulkan is set up by creating a VK pipeline object and describe the configurable state of the graphic card, like the viewport size and the depth buffer operation, and the programmable state using VK shader module object. The VK shader module objects are created from the shader bytecode. The driver also needs to know which render target will be used in the pipeline, which will be which we specify by referencing the render pass. One of the most distinctive features of Vulkan compared to existing API is that almost all configuration of the graphics pipeline needs to be set in advance. That means that if you want to switch to different shader or slightly change your vertex layout, then you need to entirely recreate the graphics pipeline. Right, that's interesting. That means that you will have to create many VK pipeline objects in advance for all different combinations you need for your rendering operations. Only some basic configurations like view size and clear color can be changed dynamically. All of these states need to be described explicitly. There's no default color on the there, for example. Alright, so this is fucking interesting. Before you had just a single graphic pipeline, right? And that graphic pipeline, you told, hey, draw a tree, draw grass, draw the character, draw all the enemies, draw the water, and you would switch state when you draw a specific thing. So, for example, you would go like this, right? You'd go draw water. Now switch the shader and draw characters. Now switch to the shader, draw the enemies, and now switch to the shader, draw the grass and the trees and the sun and the sky and whatever, right? So you're always switching, and it was just one single pipeline. It was just one big tube. And you just keep telling it to switch on what to do, right? Switch, right? But that's not the case in Vulkan, and this is really interesting. In Vulkan, you create multiple pipelines. So this pipeline, it only, for example, renders grass. This pipeline only renders trees. This pipeline only renders, I don't know, enemies. This pipeline only renders the player, and so on and so forth, right? And so you set all these in advance, and you just use them. You cannot change them later on, which is kind of cool. If you want to change them, you have to recreate a new one directly. They can use that because you're doing the equivalent of ahead of time compilation versus just in time compilation. There's more optimization policy for the okay, cool. So because you're telling the driver everything that you're doing ahead of time, it kind of knows what it's supposed to do, and it can optimize things, which is kind of cool. Oh, almost done. Oh, we're almost done, guys. Only 900 billion fucking steps. Alright, command pools and command buffers. As mentioned earlier, many of the operations of Vulkan that we want to execute, like drawing operations, need to be submitted to a queue. These operations first need to be recorded into a VK command buffer. Sure. Before they can be submitted. These command buffers are allocated from the command pool that associate the specific queue family. To draw a simple triangle, we need to record command buffer in the following operation: begin the render pass, bind the graphics pipeline, draw 3 vertices, and the render pass. Because the image in the frame buffer depends on which specific image the swap chain will give us, we need to record the command buffer for each possible image and select the right one at draw time. Alternative would be to record the command buffer again every frame, which is not efficient. What? Because the image in the frame buffer depends on which specific image a swap chain will give us, we'll need to record command buffer for each possible image and select the right one at draw time. What the fuck? Okay, sure. Interesting. I don't quite sure how. Okay, we'll figure out that, I guess, later on. The main loop. Now that drawing commands have been wrapped into command buffer, the main loop is quite straightforward. We first acquire an image from the swap chain. Easy. We can select the appropriate command buffer that the image and execute it with VK. Easy. Finally, return the image to swap chain for presenting the screen. Easy. Operations that are submitted to the queue are executed asynchronously. Therefore, we have to use asynchronization objects like semaphores to ensure that the correct order of execution. Execution of the draw command buffer must be set up to wait on image acquisition to finish. Otherwise, it may occur that the start rendering of an image is still being read for presentation on the screen. The VKQ present call turns need to wait for rendering to be finished, for which they used second semaphore that signaling the rendering completes. Alright, cool. That's exciting. This whirlwind tour should give you a basic understanding of the work ahead of drawing the first triangle. A real world program contains more steps like allocate there's more steps like allocating a vertex buffer, creating uniform buffers, and uploading textures, images that will convey in subsequent chapter. We will start simple because Vulkan has enough of steep learning curve as is. Know that we'll cheat a bit by initially embedding the vertex coordinates in the vertex shader instead of using the vertex buffer. Oh fuck, really? That's because managing vertex buffers requires some familiarity with the command buffers first. So in short, to draw our first triangle, we need to, oh Jesus fuck, create a VK instance. Done. Select the supported graphics card. Done. Create the, why am I saying done? It's not like we've fucking done anything. Create a VK device and a VK queue for drawing and presenting. Okay. Create a window and a window surface swap chain. Lovely. Wrap the swap chain image into VK image view. Create a render pass that specifies the render target and usage. Create the frame buffer for the render pass. Set up the graphics pipeline. Allocate and record the command buffer with the draw command for every possible swap chain image. This scares me. This fucking scares me. What the fuck? Okay, sure. This scares me. Draw frame by acquiring image, submitting the right command buffer, and returning the image back to the swap chain. It's a lot of steps, but the purpose of each individual step will be made very simple, clear in upcoming chapters. If you're confused about relation of single step compared to the whole program, you should refer back to this chapter. Lovely. API concepts. This chapter will conclude with a short overview of Vulkan API structure. Okay, coding conventions. All of the Vulkan functions, enumeration, and structures are defined in the vulkan.h header, which is included in the Vulkan SDK developer. Blah, 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 blah. Okay, cool. Functions have lowercase vk prefix. Types like enumeration structures have a vk. Okay, prefix. And values are vk underscore. The API heavily uses structure to provide parameters. Okay, for example. So vk, this is our lovely structure. This is our value. And this is our object or structure again. This is our numerator. Quote or value or fuck you want. Yeah, it's value, really. Lovely. Okay, so many structures of Vulkan require you to explicitly specify the type of structure in S type. Member. Of what kind of structure we're creating, okay? The pnext member can point to an extension structure will be used on Nulpter. The story function that creates destroyed object will have allocation callback. I'll just custom allocate driver from memory, which also left Nulpter. Okay. Wait, what? Functions that create or destroy objects will have a VK allocation callbacks parameter that allow you to use custom allocators for driver memory, which will be left null for this tutorial. Alright. Almost all functions. Why not all functions? Why almost? Return a VK result that is their success. Okay, so this is straightforward. This is pretty straightforward. You have a structure, you fill it with information, you call it create to create the thing. If successful, it passes. If it fails, then it fails. Oh, validation layers. As mentioned earlier, Vulkan is designed for high performance and low driver overhead. Therefore, it will include very limited error checking and debugging capabilities by default. The driver will often crash instead of returning an error code if you do something wrong. Or worse, it will appear to work on your graphic card and completely fail on others. Vulkan allows you to enable extensive checks through the feature known as validation layer. Validation layers are pieces of code that can be inserted between API and the graphics driver to do things like returning extra checks on functions parameter and tracking memory management problems. The nice thing is that you can enable them during development and then completely disable them, reducing the application for zero overhead. Anyone can write their own validation layers, but the Vulkan SDK by LunarG provide the standard set of validation layers that we'll be using in this tutorial. Jesus Christ. You can also register a callback function to receive debug message from the layer. Because Vulkan is so explicit about every operation and the validation layer are so extensive, it can actually be a lot easier to find out why your screen is black compared to OpenGL and DirectX. There are only one more step in this chapter, which is setting up development environment. Whew. Alright, so my body is ready. 3 years ago. I wonder if you did it, man. Amazing tutorial. Thanks for the awesome tutorial. Ah, nice. Thanks. Very good. Thanks. Best tutorial out there. I have Battlefield. I know what you mean, buddy. Officially, okay, cool. It's nice. Hello. Oh, hi there. We can select appropriate command. Alright. Oh god. Why am I doing this? I could just use Unity. Funny. Oh god. Oh no. Oh no. Ooh, I can do this on Mac? It supports Vulkan now? Oh, that's hot. Does Vulkan officially support him? Is supporting on Mac? Apparently, Vulkan. Oh, that's cool. That's well, the Vulkan crew. The Vulkan group announced the updated Vulkan scale include finally, including Silicon and Apple. With Apple still not officially backing Vulkan, but preferring their own closed ecosystem of Metal API, Vulkan OS platform continues to rely on Molten VK portability layer that ultimately routes Vulkan over to Metal driver. Oh, motherfuckers, just write it in fucking Metal. Why? With Vulkan's DNA firmly available in our top is on Mac OS and games and developers. Okay, cool. Alright, so that's bullshit. Thank you, Apple, for being fucking dickheads. Alright, cool. Alright, so let's do this. Let's set up our development environment. I think we're gonna do this. I'm just gonna set up my environment, development environment, and then call it for tonight because it's almost 11. And, well, it's kind of late, you know. In this chapter, we'll set up your development environment for developing Vulkan applications, installing some useful binaries. All these tools will be used, etc. Cool. Windows. If you're developing, they're assuming you're using Visual Studio to compile your code. Yes. You'll need first. Okay, nice. Thank you. Vulkan SDK. The most important component you'll need for developing Vulkan application is the SDK. Woo! It includes headers and standard validation layer, debugging tools, and load of okay, cool. The Vulkan looks up. If you're familiar with it, nice. SDK can be downloaded here. Oh, cool. Let's go and download the SDK. Woo! Vulkan SDK. We wanna download the Windows version of the Vulkan SDK. Gonna zoom in cause I can't fucking see anything. September 15th. Ooh, oh, all the versions. Nice. Or most of the versions. Alright, so we're gonna download the latest one. There's the SDK, SDK config, runtime, and the runtime config. I'm just gonna do the SDK right here. 105 whole MBs? 105? That's a lot of MBs. Okay, while this downloads, you don't have to create an account. You'll get no, cool. Proceed through the installation and pay attention to the installation. The first thing you do is verify the graphics card. Okay, cool. Oh, Lunar GD settings. Cool. Welcome to the Vulkan. You guys can see this, but you know, I'm gonna get my magnifier so you can see what the hell is going on. La 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 la. Next. Retrieving metadata. This new module SDK is not compatible with the SDK installer prior to 1.2.189. If you have installed one or more of the newer SDK or newer and you wish to install the older SDK prior to 1.2, you must uninstall or okay, I didn't install anything. To install the most recent SDK and okay, cool. I don't have this fresh install. Yes. Oh Jesus. Okay. Optional. We don't want 32-bit. Debug share library. Yes, let's do that. We don't want 32-bit. Third-party libraries and headers. Sure. Why not? I mean, that could always be useful. We don't want to do 32-bit. Next. I acknowledge. I have acknowledged your acknowledgement. Okay. 2.71 GBs. Oh no, what are we gonna do? It's a lot of GBs. Oh, so hold on, let me get this straight. I downloaded 105 MB off of the internet, so you can go ahead and download 113 MB out of the internet. So what the hell is the 105 was for? Alright, sure, I suppose. You know, not complaining. Kinda complaining, but, you know, not complaining. Kinda complaining. But not complaining. It's kinda complaining. It's not complaining. Kinda complaining. Okay, I'm gonna stop now. Sorry. Vulkan, 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 Vulkan. Woo! We finished! Okay. Where's the thing? The new module SDK is talking about. Oh my god, I know you said that already. Alright, thank you for letting me know. I appreciate your help. Directly, okay, let's go to the SDK and open this and see if it works. I do have a nice graphics card, I believe, if I'm not mistaken. Alright, so I have a 69 XT. It does stuff. It goes vroom vroom. And I do have the latest driver. Zzz. And as far as I know, you do support Vulkan. Performance. Where can I see video? Account devices. Cool. Why am I opening this? This makes no sense. Okay, cool. Let's go to the SDK. Vulkan. Bin. What do you want me to open? VK Cube. Fuck is VK Cube? Let's see. Oh, beautiful. A beautiful cube. It's very cubey. It's going in circle. It's textured. It's running. It's beautiful. Absolutely beautiful. All right. Well, that's good. If you receive an error, I don't receive an error. Shut the fuck up. Moving on. There's another program in directory will be useful in development. The GLCell and GLCell lang validator.exe and the glslc.exe program will be used to compile shares in a human readable GLCell bytecode. We'll cover this in depth in share modules chapter. The bin directory also contains binaries of Vulkan load validation layers like blah blah blah. Cool. Lastly, there's the include directory that contains the headers. Feel free to explore these files, but won't need them in this tutorial. Alright. GLFW. As mentioned before, Vulkan itself is a platform agnostic API. It does not include tools for creating a window to display the benefits from the cross-platform adventure of Vulkan is need to avoid the horror of Winter 2. Ooh, so scary. We'll use the GLFW create. I mean, we already went through the horrors of creating Winter 2. I mean, not really, but you need to still create a pixel format. It's a whole thing. So, okay, cool. You can find the latest GL. I don't care. GLM. Unlike DirectX 12, Vulkan does not include a library for linear algebra operations. Why am I talking like that? So we'll have to download GLM. We're gonna create our own math library. So fuck off. All right. Setting up Visual Studio. Ooh, Visual Studio. Oh my god, crazy talk. That's okay. Okay. Main. Oh, Jesus. Okay, we need the includes. We need GLM. Alright, so we need the includes. Oh, God. Give me strength. I have zero idea what in the flying fuck I'm doing. Alright, so we want to go to our engine. In our repository, we need to create a folder that's called libs. In the libs folder, we'll create another folder called Vulkan. In the Vulkan directory, we are gonna create a folder that has the value 1.2 point whatever the fuck it is. Yes, open it up, copy the includes and paste them in the directory. Yes, 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 yes. Very cool. We're gonna do that. And after we do that, we are gonna go to the linker, edit the linker. Oh, we need to include the libs folder. How can I forget the libs folder? Motherfuck, how big is this? Oh, Jesus, 2.6 GB. Oh, what the flying shit? Why? Oh, no. What's so big? 122 MB. Oh my god. You are tremendously large. You are tremendously, absolutely, unequivocally large in terms of megabytes and gigabytes. Oh Jesus, this is really fucking big. That's what she said. Yeah. So goddamn funny. Alright, I need to include this or link this. So let's do this. So I'll go to core. Gotta link this baby up. Link it and shrink it. Why did I do that? I need to link my libs. My libby. Include. I need to include the includes. You're gonna be copy. I need to zoom for you guys so you can see what in the flying fuck I'm doing. Includes. We're gonna include in our includes project name. There's no build. This is gonna be called libs. Is it libs or lib or the fuck is it called? And it's gonna be called libs, and inside libs there's Vulkan. Let's do that. Libs slash that Vulkan slash this. Can we focus here? So libs slash Vulkan. Inside Vulkan is the version number which exists over here slash lib and include. Oh, these are capital. Oh, how fancy. How glorious. Absolutely fantastic. Absolute peach. Include. So it's going to be, let's verify this is correct. So it's going to be conta source repo Vulkan engine libs Vulkan 1.2 point whatever includes. There you go. See how easy that was? See how easy that was? It's very easy. Libraries, we're gonna do that. Instead of includes, we're gonna have libs or just lib, right? Isn't it called lib? Libby. Yep, the libby. Apply that. We linked everything. Everything is done. Everything is donezo, my friend. As they say, donezo bonzo. C++ standard 17. Why are we using 17? Sure, why the fuck not? Let's use 17. Excuse me, sir. I would like to use the Windows 17 version. I mean, C++ 17, if you don't mind. If your holiness and gloriness don't mind, can we please do that? Oh, thank you. Thank you, sir. Thank you very much. Thank you. Alright, so we use 17, sure. 64-bit, obviously. Duh. Who the fuck uses 32? Here, if you did everything, then you should no longer see it. Okay. Cool. Linux. I don't use Linux. Fuck Linux. Actually, Linux is pretty cool. Not fuck Linux. Linux is good. Don't care. I'll share. They're just about only setting apart. I don't know how to do that. I don't care. This is all Linux stuff. Mac OS. Vulkan SDK. Alright, the most important recommendation in Vulkan application SDK is to include the headers and standards and revelations. If you're familiar with it, okay, sure. That's again, okay, cool, with deadline. Version. Oh, this is Mac OS. Why are we doing this again? Why are we doing the same thing again? Why? Alright, we set up our environment, boys. Boys and girls. Fellas and fellas. Alright, can we do a quick test to make sure this Vulkan is actually initialized? Can we just copy something and oh, okay. This is gonna be a little bit tricky because these guys, they don't tell you how to create how to communicate the window thing, right? So can you just give me the full code so I can just copy it? So I just want to copy part of this, so I just can test it to make sure everything's working. So copy off that, paste it over here in the engine after creating the window. Yes, sir, Bob. Actually, yeah, sure, why the fuck not? Alright, it's gonna complain, it's gonna bitch. I know. I get you, man. I get you. We're all on very different things. You know, we're all very Vulkan.h. Alright, then I assume that's all I need to do here. Don't give a fuck about any of that. Don't give a fuck about any of that. And I need my instance. Where my goddamn instance? Sorry. Here we go. Here's my instance. I love the Vulkan instance. It makes me want to fly so high above the fucking sky. Ooh, I'd be on air. No such directory existing in the air. Why the fuck not? Rebuild this. Let's see if this works. Okay, so the code works, but building the sandbox is not very happy because it doesn't know where Vulkan exists, right? So we need to include what we did in here over there. So yeah, so I'm going to have the includes over here. La 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 no 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 no. Alright, so my sandbox needs to also include these. Which is interesting, sir. It's very interesting to say the least. I'm telling you, sir. That's very interesting. Can you work? Well, oh, it worked. Can I build it? Hooray, it works. Does this actually, so it compiles on everything. It doesn't like, you know, doesn't go not so but so. Alright, blah blah. Oh, and it creates the instance. So if Vulkan is not successful, else cout created instance of Vulkan correctly. Vulkan. Alright, let's run this baby. And it should say created a Vulkan instance correctly. Hello, sir. There you go. So Vulkan is linked correctly. I can go delete all this crap. Right? this was just a test, just to test things out. I can delete this shit over here. Right, we don't need it. We don't need this fake instance thing. Rebuild everything. Make sure everything's running correctly without the Vulkan stuff. After removing them, obviously, duh. Run this up. This is working. All right, cool. So we linked Vulkan. We have our environment all set up, which is great. And to tell you the truth, that is all I'm capable of tonight. I'm kind of tired. And to make this work is going to be a nightmare because we need somehow to be able to communicate with the windowing system. Because this tutorial is specifically talking with JLFW, and we're not using JLFW, so this should be interesting. I have no idea how to put that. Cool. So this is another good session. So today we did like 4 or 5 hours of work on Vulkan, on the engine. 3 separate sessions, which were decent, very decent sessions, I would say. Yeah, that's it. I'm gonna go do something. I don't know, play maybe Final Fantasy before I go to bed. And then yeah, I hope you guys have a fantastic day, week, month. I don't know. And yeah, see you. Take care. Bye bye.